From a distance, Enceladus looks like nothing. A perfect white sphere, roughly the size of Arizona, drifting quietly in Saturn's shadow. No craters, no scars, no obvious signs of violence. It is the most reflective object in the solar system. So bright, it was mistaken for a star when astronomers first cataloged it in the 18th century. It looks dead. It looks clean. It looks safe. It is none of those things. When NASA's Cassini spacecraft made its first close pass of Enceladus' south pole in 2005, the instruments recorded something that stopped the mission team cold. The temperature data was wrong. Not slightly wrong, catastrophically wrong. There was heat radiating from a moon that had no business generating heat. And then the cameras caught it, enormous plumes of water vapor and ice erupting from the surface, shooting material 500 kilometers into space and directly into Saturn's rings. Enceladus wasn't dead. It was screaming. In this video, we are going to reveal 3 things that will permanently change how you see this moon. We will expose what Cassini found when it flew directly through those geysers. We will show you what is happening at the bottom of a dark ocean that has been sealed under kilometers of ice for potentially hundreds of millions of years. And we will explain why a discovery in 2023 turned the question of life on Enceladus from scientific curiosity into something researchers can no longer sidestep. Let us start with the day this frozen moon announced itself to the world. For years, planetary scientists categorized Enceladus the way you would categorize a pebble on a driveway. It was small, cold, and considered geologically inert. At roughly 504 kilometers in diameter, barely the width of a mid-sized American state, it was thought to be too small to sustain internal activity. Internal heat requires mass, and Enceladus had almost none. The prevailing model was straightforward. The moon had frozen solid billions of years ago, its surface locked under a featureless shell of ice, and nothing of scientific consequence had happened since. It was, in the clinical language of planetary science, dead. That model died in February 2005. As Cassini made its first close flyby of Enceladus' south pole, its instruments began recording warmth that had no right to exist. Then the cameras resolved something that would trigger a complete rethinking of icy moon science. 4 enormous fractures stretched across the south polar terrain, each 130 kilometers long. Scientists nicknamed them the Tiger Stripes, and from those stripes, Enceladus was erupting. The geysers were not subtle. Water vapor, ice particles, and organic compounds were jetting from the fractures and climbing 500 kilometers above the surface. To feel the scale, 500 kilometers is the distance from New York to Boston, rising straight up from a moon the size of Arizona. And the material wasn't drifting, it was exiting at over 400 meters per second. For context, Enceladus' escape velocity is only about 240 meters per second. The plumes weren't just erupting, they were escaping, punching through this moon's gravitational grip entirely and seeding directly into Saturn's E-ring. Saturn's rings contain material from Enceladus' interior. Whatever is inside that moon has been spraying into Saturn's ring system, possibly for millions of years. In subsequent flybys, Cassini flew directly through the plumes and sampled them. The results, published by Carolyn Porco and the Cassini imaging team in the journal Science in 2006, confirmed water vapor, molecular salts, and organic compounds, not a frozen rock exhaling ice crystals, an active interior venting its own chemistry into space. If you were standing on Enceladus' surface during one of those eruptions, the experience would be unlike anything else in the solar system. The radiation environment near Enceladus is relatively mild, unlike Europa, which sits deep within Saturn's radiation belts. Radiation is not the primary threat. What would kill you is the temperature. The open surface averages minus 201 degrees Celsius. Without insulated equipment, your survival time can be measured in seconds. And the gravity, roughly 1% of Earth's, means the surface barely holds you. Enceladus's escape velocity is achievable by a human being running at moderate speed. The moon would let you drift off the surface. It simply wouldn't give you anywhere to go. But the geysers were just the first door opening. The real question was what was behind it. The first assumption that collapsed was temperature. The second was structure. Planetary scientists had always understood that liquid water requires sustained heat. Enceladus, small and distant from the Sun, appeared to have no reliable source of it. But the Cassini measurements told a different story. The surface temperature at the Tiger Stripe fractures was measuring approximately minus 93 degrees Celsius, cold by any human standard, but extraordinarily warm for a moon whose average surface sits at minus 201 degrees. The total thermal output from Enceladus's south polar region was later measured at approximately 15.8 gigawatts, far exceeding what tidal heating models had predicted for a body of Enceladus's size. Tidal heating occurs when Saturn's immense gravity repeatedly flexes and compresses at Enceladus as it orbits, the same mechanism that drives Io's volcanic catastrophe around Jupiter, but quieter, more focused, and channeled into something entirely different. That internal friction was generating far more warmth than the models allowed, and that warmth was maintaining something liquid underground. Over the years that followed, Cassini conducted systematic close flybys of Enceladus, measuring precise gravitational variations each time it passed overhead. In 2014, those measurements confirmed a substantial liquid body beneath the south polar terrain. In 2015, a more complete analysis revealed something larger, not a localized pocket of slush, not a regional lake, but a global ocean, a body of liquid water completely encircling Enceladus's rocky core, sealed beneath an ice shell roughly 20 to 25 kilometers thick across most of the moon, thinning to perhaps a few kilometers at the Tiger Stripes. The findings were published by Peter Thomas and colleagues in 2016 in the journal Icarus, confirmed through precise measurements of Enceladus's orbital libration, a subtle, repeating wobble that is only possible if the moon's ice shell is decoupled from its interior by a continuous liquid layer. Let that settle. Beneath an ice ceiling thicker than the deepest point of Earth's ocean, in complete darkness, under pressure, with no sunlight and no surface, there is a global ocean in direct contact with a rocky sea floor. It has potentially been there for hundreds of millions of years, sealed, chemically active, evolving in isolation. Not everyone agrees on the timeline. Some planetary scientists have argued that Enceladus's current activity may be episodic, geologically recent, perhaps only tens of millions of years old, rather than billions, a temporary phase in a long, quiet history. That debate continues, and it matters. But even the conservative estimate, tens of millions of years of dark, warm, chemically active ocean, represents a window of time so vast it defies intuitive comprehension. And at the bottom of that ocean, the data shows something extraordinary was happening. Here is what we know about the origin of life on Earth. The most compelling scientific hypothesis is not that life began in a warm pond baked by sunlight. It is that life began in total darkness, at the bottom of the ocean, at hydrothermal vents, fractures in the sea floor, where superheated water, driven upward through rock, meets the cold, deep ocean above. These systems produce molecular hydrogen. They generate organic chemistry. They create alkaline chemical gradients that store energy the way a battery stores electrical charge. And they require no sunlight at all. Life at these vents does not need the surface. It does not need the sun. It needs chemistry, heat, and water. In 2015, Hans Werner Schuh and a team of researchers published a study in Nature analyzing the silica-rich nanoparticles that Cassini had been detecting in Saturn's E-ring for years. These particles are highly specific. They form only when water at temperatures exceeding 90 degrees Celsius reacts with rock, a process called silica precipitation that occurs at hydrothermal vents. On Earth, they form at the seafloor, and in the Saturn system, there is exactly one location where the temperature, the chemistry, and the water-rock interaction could produce them: the floor of Enceladus's ocean. Those tiny particles, drifting through Saturn's rings for years before Cassini identified them, were physical evidence of an active hydrothermal system operating at the bottom of a moon we nearly wrote off as a frozen rock. Then in 2017, during one of Cassini's final deliberate close passes through the Enceladus plumes, the spacecraft's ion and neutral mass spectrometer registered molecular hydrogen at concentrations between 0.4 and 1.4% by volume. Hunter Waite of the Southwest Research Institute, lead author of the study published in Science that year, was precise in his assessment. This hydrogen was not generated by the plumes themselves. It was generated by serpentinization, the chemical reaction that occurs when hot water meets rock at the seafloor. Serpentinization is the same process that powers the Lost City hydrothermal field on Earth's mid-Atlantic ridge, one of the most chemically active, biologically rich environments on this planet, where life thrives in complete darkness entirely on chemical energy. Scientists consider environments like the Lost City among the most plausible birthplaces of life on Earth. Enceladus has one, running independently, in the outer solar system, on a moon the size of Arizona. This is not theory. This is what the instruments measured. Chemical energy is being generated at Enceladus's seafloor right now, through the same mechanism that may have produced life on Earth. The water is there. The organic chemistry is there. The energy source is there. And by 2017, the scientific community had quietly acknowledged that Enceladus checked every box scientists had identified as necessary for life, with one exception. One ingredient remained unconfirmed, and it was the most important one. Life, as we understand it, requires 6 elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. This set, abbreviated CHNOPS in astrobiology, is not a preference, it is a structural requirement. These 6 elements form the molecular architecture of every living thing we have ever observed. Carbon builds the backbone of biological molecules. Hydrogen and oxygen form water. Nitrogen is in amino acids and DNA. Sulfur is in proteins and metabolic enzymes. And phosphorus is in a category of its own. It is the backbone of DNA and RNA, the molecules that carry and express biological information. It is the core of ATP, the compound all known life uses to store and transfer energy at the cellular level. Without phosphorus, the chemistry of life cannot assemble itself. Its absence was the single remaining scientific reason to maintain caution about Enceladus. In 2023, that reason disappeared. Frank Postberg of Freie Universität Berlin and an international research team published a study in Nature reporting the detection of phosphates, the bioavailable form of phosphorus embedded in ice grains analyzed by Cassini's cosmic dust analyzer. Those grains came directly from Enceladus's plumes. They originated in Enceladus's ocean. Their estimated concentration was at least 100 times higher than in Earth's own oceans. Every element required for life as we understand it is now confirmed present in Enceladus's subsurface ocean. All 6 are there, in a body of liquid water, in contact with an active hydrothermal seafloor with organic chemistry already circulating, and given potentially hundreds of millions of years to run. This is the point at which the question changes. The previous scientific posture, that Enceladus might have conditions capable of supporting life, no longer accurately describes what the data shows. The harder question, the one scientists are now actually grappling with, is this. Given that every ingredient we have ever identified as necessary for life is present in abundance, and given that on Earth those ingredients produce life in every environment where they coexist, what is the specific mechanism by which life failed to emerge on Enceladus? There is no clean answer. Some researchers argue that the origin of life, even given perfect conditions, may be rare enough that most favorable environments remain lifeless, that the step from chemistry to biology is the hardest transition in the universe. Others argue that the chemistry essentially guarantees biological output given enough time, and that we should already expect microbial life in Enceladus's ocean, waiting for instruments sophisticated enough to detect it. That debate, which is at its core a question about how common life is in a universe of trillions of worlds, remains unresolved. Enceladus has become the most critical test case we have ever had. Right now, material from that ocean is erupting through fractures in the ice and drifting through Saturn's ring system. If anything biological exists in those waters, its chemistry is already distributed across the rings. Saturn's rings may hold the answer. We are only beginning to learn how to read them. So what does all of this mean? We know that a small, bright moon, dismissed for decades as geologically irrelevant, contains a global ocean of liquid water sealed beneath kilometers of ice. We know that ocean sits above a rocky seafloor where hydrothermal vents are actively generating chemical energy. We know that ocean contains every element required for life. And we know that material from that ocean is erupting through fractures in the surface and drifting through Saturn's rings right now. If life exists in that ocean, even microscopic life, even something so simple it barely qualifies as alive, it changes the equation for the rest of the universe. It means that when the right conditions come together, life appears. It means that in a cosmos with trillions of planets and moons, the silence we thought surrounded us was never silence at all. It means we were never alone, and we simply didn't know how to look. If life does not exist on Enceladus, despite every ingredient being present in concentrations that exceed Earth's own oceans, then something fundamental is missing. From our understanding of biology, the distance between chemistry and life is larger than we calculated. The silence is real, and it is everywhere. Both possibilities are extraordinary. Both are terrifying. Both would be the most important discovery our species has ever made. When you look at Saturn in the night sky, that quiet, steady point of gold above the horizon, you're looking at a planet circled by a moon that has been holding an ocean in the dark for hundreds of millions of years, indifferent to whether we find it, indifferent to what we discover inside it, indifferent to whether we ever learn to ask the question at all. We are asking it now. That might be the most remarkable thing our species has ever done. If you want to know what else the solar system is hiding, watch this next.